Okay, so today we're going to begin probably about a 2-week discussion, 4 classes, I would say minimum, on the Neoclassical Growth Model. This is, I guess, the companion model to the optimal growth model that we just got done talking about. So same kinds of outcomes are going to emerge in this model, but the economic environment is different. Instead of a social planner's problem, we're going to look at it from the perspective of a kind of a decentralized equilibrium. The model differs from really the solo growth model in only one kind of crucial way, and that it explicitly models the consumer side and it endogenizes the savings rate. Whereas the savings rate is constant and exogenous in the solo model, it is going to be endogenous in the neoclassical growth model. And so it obviously has household optimization as its kind of roots. We'll build up the model from those foundations. We're obviously going to look at this model just from the perspective of another type of growth model, okay? But for those of you who go on to take the second PhD macro course in the spring, you're going to quickly realize that this model forms the foundation. It's kind of the workhorse model that is used to this day for lots of different types of exercises. For instance, business cycles. So business cycle modeling uses the neoclassical structure as its foundation for the most part. Analyses of fiscal and monetary policy also utilize the neoclassical model as a workhorse. So talking about optimal monetary policy and optimal fiscal policy is done from this kind of core framework as well. Of course, the newest models are going to be somewhat more complicated and feature additional frictions and pieces to the structure that differ from what we're going to talk about today. But at its core, it resembles the neoclassical growth model. Okay, so what's the plan for today's discussion? I really want to just do 2 things. First part of the talk today is just to discuss the basic preferences and technologies and demographics of the neoclassical model. So just kind of set up the environment. Who are the agents that populate the economy, and kind of how do they behave? What are their incentives? What problems are they trying to solve? And then hopefully I'll get to spend most of the time talking about a key component of the neoclassical model that is going to be new, and that is the intertemporal budget constraint. So we're going to talk about the budget constraint, and in particular how it relates to 2 types of conditions that we're going to have to place on this model that are different from the infinite horizon models we've talked about in the past. One is what's called a natural debt limit, and the other that we can use as an alternative to the natural debt limit is a constraint called the no Ponzi gain condition. These are constraints that have to be imposed on the neoclassical model in order for a unique, stable solution to exist. And they're constraints that are new to this model relative to what we saw in the optimal growth model. So I'm going to spend a great deal of time today talking about the natural debt limit as well as the no Ponzi gain condition, and how those 2 things relate to the representative family's lifetime budget constraint. Okay, there's a key connection there that I want to try to establish. All right, any questions in before we get started? All right, let's first talk about preferences, technologies, and demographics. All right, so first off, let's talk about the households. Those are the key agents of the model. The firms in this model behave just the same as they have in other models past. All right, we're going to consider an infinite horizon economy. Okay, so agents live forever here in discrete time, and the economy is going to admit a normative representative household, okay? And that representative household has the following utility function, U of CT, okay? Now this brings me to assumption 1 in the notes. The utility function is going to be defined on the positive reals less 0, and it maps elements of that space into the real line. It is strictly increasing and concave and twice differentiable. So U prime of C is positive, U double prime of C is negative. All right, so the period utility function exists over strictly positive values of consumption. It's strictly increasing and concave, and it's continuously differentiable, all in the interior of its domain. Okay, now to be specific about who's actually populating the household sector, really what's happening here in this model is that I want you guys to think of this in terms of a continuum of households, okay, of measure 1. So we can think of all the households living on the unit interval 0 to 1, okay? So there's a measure 1 or a unit measure of households. And each of those households has the same normative utility function given by U of C, okay? Now, each household or each family, if you want to think about it, has the same type of population that grows at the same rate, okay? So we're going to assume that the size of the population is normalized to 1 in the initial period, okay? And that after that, population of each household grows at rate n, okay? So that means then at date t, the size of the population is just equal to 1 plus n raised to the t times L0, right? We have standard exponential growth in population. And of course, if L0 is normalized to 1, then that means the population at time t is just 1 plus n raised to the power of t, right? Or LT is equal to 1 plus n times LT minus 1. Okay, now just like the optimal growth model, all members of the household or of the representative family supply 1 unit of labor to the workforce inelastically. So again, there is no labor leisure choice in this model. All right. The household is fully altruistic towards all of its future members. And it always makes allocations of consumption among its members cooperatively. All right. So that means it's essentially going to distribute consumption equally to all members of the family every single period. That's basically all we're saying there, okay? So this isn't going to be a heterogeneous agent model where some agents get more consumption than others. It's a representative agent model where the head of the household, the family boss, distributes consumption equally to all members of the representative family, okay? All right, if CT is aggregate consumption or family-wide consumption, if we divide that by the number of members in the family or divide that by the population, you get per capita consumption, little c. Okay, make sure we're distinguishing between these different variables here. All right, so the total utility then for the representative family then can be defined as the number of members of the population or the family times the utility of each individual member, where this is little c or per capita consumption. Well, LT is equal to 1 plus n raised to the t. So total utility is 1 plus n to the t times U of C. Okay, now let me define rho as the household's subjective discount rate. It's not the discount factor, it's the subjective discount rate. So the lifetime utility then of the representative family is the sum from 0 to infinity of 1 over 1 plus rho. So 1 over 1 plus rho is more related to the discount factor raised to the t times the total utility of the family in period t. So that's LT times U of CT. Well, we just talked about how LT is equal to 1 plus n to the t. So I'm going to shove that term inside of the discount rate here, and that becomes the sum from 0 to infinity of 1 plus n over 1 plus rho to the t times U of CT. I'm going to define this term here as beta. So 1 plus n over 1 plus rho is the effective discount factor in this model. So that way, lifetime utility has the same form as it did in the optimal growth model, correct? Where it's the sum of beta to the t times UC. Now this brings me to assumption 2, which is seems like an innocuous assumption, but it is actually critical to establishing the existence, uniqueness, and stability of the equilibrium in this model. And it regards beta. What do we know is true about, or what do we know has to be true about beta? If it's a discount factor, it needs to actually discount. So it needs to be less than 1, right? So in order for beta to be less than 1, what has to be true? N must be bigger than, rho must be bigger than n. So the subjective discount rate rho has to be bigger than the population growth rate. That's the only way in which you get beta between 0 and 1. We will see that situations in which the discount rate falls short of the population growth rate will lead to instability in this model, or it will lead to the existence of not a stable, unique equilibrium. We have to have rho bigger than n in order to utilize our stationary dynamic programming theorems that we discussed earlier. Okay? All right, does everybody see how the household sector is set up then? It's a representative family with this kind of continuum of members. The population grows at a standard rate n. Everybody receives the same consumption. You can think of resources as being pooled every period and distributed equally to all members of the representative family. And that the population growth rate has to be less than the discount, or the subjective discount rate rho. Okay, what about firms? Here, the story is basically the same as before. Factor and product markets are going to be perfectly competitive, okay? The production function of each of these firms is going to be identical, and so we can aggregate the production function into a standard neoclassical form, where output y is equal to a function f of the capital stock and labor, or the total size of the population, if everybody's working one period. Notice I haven't put any technological progress here, so I'm abstracting from that. You can go and stick in an A term there, or exogenous technological progress, and work through the model. I'm sure there's a review question that does that. The production function satisfies all of our neoclassical assumptions. It's strictly increasing in K and L, it's differentiable, it's strictly concave, it satisfies the anodic conditions, blah, 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 blah. All of that carries over from day one of this course. The fact that F is linearly homogeneous, that it exhibits constant returns to scale, implies that we can rewrite the production function in its per worker or intensive form, right? Where y over L is a function of f of k over L and L over L. In other words, output per worker can be written as a function of just capital per worker. All of that, again, is exactly the same as before. The factor markets are competitive. So the real rental rate of capital is just going to be equal to the marginal product of capital, which we know is just the slope of the per worker production function. The real wage is equal to the marginal product of labor, which in terms of capital per worker, you'll recall is just equal to F of K minus K times F prime of K. Okay. All right, any questions so far? Let's get to something new now. So we've talked about households and we talked about firms. Let's now talk about the budget constraint facing the representative family. So here things are considerably different. Remember, in the optimal growth model, a benevolent planner was deciding on what the allocations were going to be across the population. She was constrained by the resource constraint of the economy. There are no markets, right? Here in this model, markets determine allocations. And so families are constrained by their period by period income constraints. Okay, now what does that budget or income constraint look like for the representative family? Let me define some new notation. Capital A, but don't get confused, this is not technology. This is going to be family assets at date T. So the family has some stock of assets denoted AT, real assets denoted AT at period T. Now, you can already imagine in this economy, the only type of asset that is tradable is going to be the stock of physical capital. So in equilibrium, A and K are going to be equivalent to one another. But when considering just the family's optimization problem, we want to abstract from that connection and just consider the family's asset position, okay? AT is how many real assets the family has accumulated at the beginning of period T. It is a state variable from the perspective of the family who is going to be maximizing lifetime utility. Okay, now how does the family's portfolio of assets evolve over time? In other words, the family's net additions to its stock of assets or its portfolio of assets is going to be what? It's going to be the real return on its stock of assets that it has during period T. So R is the risk-free rate of return on that asset, plus all of the labor income that the family earns, so the real wage times L, minus what the family decides to consume collectively. This is the law of motion for the family's portfolio of assets, right? The family will add to its stock of assets. So the change in assets here will be positive if its income from work and investments exceed what it spends on consumption. If it has some savings left over, in other words, it's going to add to its portfolio of assets. That's AT plus 1 minus AT. Again, RT is the risk-free market rate of return. You can imagine it's going to be related to the real rental rate on the capital stock in a competitive equilibrium, net of the depreciation rate. Okay, again, we're going to impose those conditions ex post on the equilibrium. Right now, we're really just thinking about the family's problem, and this is the budget constraint that the family faces. Okay, questions about the asset accumulation equation here for the household, representative household. Okay, now just like we did with the production function, it will ultimately be easier for us to work with intensive form variables. These are the variables that will be stationary in an equilibrium, right? So what if I divide everything by LT here? What am I going to be left with? Well, what is AT plus 1 over LT? You guys remember this trick. It's going to be AT plus 1 over LT plus 1 times LT plus 1 over LT. So that would be little at plus 1 times 1 plus n, where little a is just big A over L, right? Minus little a is equal to R times little a plus, let's see, W times L over L is just W, minus C times L over L is just C. This is the per worker asset accumulation equation, right? The change, or the net change in the individual's asset position is just equal to the returns to those assets plus labor income minus what that individual consumes. And this adjusts for the growing population. All right, if I let's see, subtract a 1 plus n times AT from both sides of the equation, you get that the change in AT plus 1 times 1 plus n would be equal to RT minus n times AT plus WT minus CT. This is the period by period budget constraint that the representative family confronts in the course of solving its maximization problem, after we've transformed the variables into their stationary form, that is the per worker form. Okay, now, again, I'll come back to this probably in the next class, but capital is the only productive asset in the economy, right? So when the family is purchasing asset shares here, these asset shares are backed by an equal quantity of physical capital. So in equilibrium, one of our equilibrium conditions is going to be that AT must be equal to KT for all time, right? That's the only type of way of transferring resources intertemporally in this world, is by investing in the capital stock. What do you think the market risk-free rate of return on assets is going to be equal to? Well, it's going to be equal to the real rental rate on capital minus the physical depreciation rate. This will also hold in equilibrium.
Also question.
Yeah.
So you're saying that also they only have physical capital, like capital in terms of like housing or some other financial capital, not in that regard.
That's not in this model specifically. Remember, this is a very stylized model. We can think of this in terms of like, corn or livestock, right? That the good that is produced can be costlessly transformed between consumption or saved in the form of investment. So this model does not distinguish between human capital or physical capital or financial capital. It's all of those things. If you want to think of K as somehow summarizing all of those things together, that would represent like a composite of those things, right? Certainly there are other growth and business cycle models that discriminate between those various types of capital, that might have a banking sector in them, right? That might have differences between human capital and physical capital. But this model does not distinguish between those two.
So what's the advantage of using an A versus a K? Is it to distinguish between the firms and the households?
Yes. So I don't want you to think of households here as buying capital directly and saving it up and renting it. They are trading. They're potentially trading in assets which are backed by capital directly. Really the reason why I want to do this, Ben, I'm going to answer your question more fully here in a few minutes, but we need to consider the case here in which households can potentially borrow, okay? And it's not as, in other words, the household's asset position is negative. If we just treat it as K from the get-go, well, we know that the capital stock can't be negative, right? So we're obviously going to rule out those positions in equilibrium, but some complications arise when we're solving the household's problem directly that we need to account for the possibility of borrowing. And of course, there are other models where households can explicitly borrow, and they do. So to make this model more consistent with those, I'm going to distinguish between assets and the stock of physical capital, but just recognize that those things have to be equal to one another in equilibrium. If there were two different, to build on what Tavoy was saying, if there were two different physical assets in this model, let's say capital and money, okay, money can be used to transfer wealth intertemporally, then the family not only has an asset accumulation decision, right, AT plus 1 minus AT, but it also has a portfolio decision. How much of their savings to devote to capital versus money, okay? So to make this workhorse model more congruent with that larger class of macroeconomic models, I'm going to distinguish those two ex ante, but then AT and KT will be the same ex post in equilibrium for this particular model. Okay, other questions? Those are good questions. All right, let me move to the second part now and discuss two new concepts to you. Maybe they're new. The natural debt limit and something called the no Ponzi condition. All right. Let me first state the representative family's sequence problem, SP, okay? Given what we know so far, this is what the representative family would attempt to do. Representative family is going to maximize the lifetime utility of the identical agents in their household. So beta to the T times U of CT. And it's going to do that by choosing sequences of consumption and asset holdings or savings. It's going to choose consumption and saving optimally over time to maximize this objective. Now, what constrains the family's optimization problem? Well, the period by period budget constraint, right? Which says that the change in AT plus 1 times 1 plus N is equal to RT minus N, AT plus WT minus CT. CT, we know, has to be greater than or equal to 0. The family's initial asset position, whether it's positive savings or debt, is given. And what else does the family take as given? Remember, the family treats factor payments, W and R, as given. So this is the statement of the representative household's lifetime consumption problem. Now, what I'm going to argue here, and hopefully, Ben, this will more directly answer your question, is that this maximization problem, this sequence problem, is not a well-defined maximization problem for the representative household. And the basic reason why it is not a well-defined problem is that without further constraints on the problem, the setup essentially allows the household to build up debt without limit. In other words, it allows the limit as t approaches infinity of AT to go to some huge negative number. Okay. Now think about why that's the case. To avoid, let's say you're the head of this household. You care about consumption, right? That's ultimately what you care about. Well, what's one way of trying to achieve basically infinite consumption? Go back up here to the sequential period by period budget constraint, right? What you could do is you could borrow a huge amount, that is make AT negative, right? But then simply roll over all of that debt into a larger amount of debt the next period, right? So an infinite amount of consumption can essentially be purchased by continuing to borrow more every period and simply using your new debt to pay off all your existing debt plus interest, plus finance additional consumption. That is what we know of as a Ponzi scheme, right? That's a Bernie Madoff Ponzi scheme, okay? My point is, there is nothing that prohibits that type of behavior on the household's sequence problem. And in fact, that would be the optimal solution, is to generate infinite consumption by borrowing forever and simply rolling over that debt indefinitely, okay? Now, that's obviously going to be an infeasible strategy in equilibrium for two reasons. One, whatever financial market that we're not modeling here explicitly to Voy is doing the lending is going to generate infinitely negative losses, right? They're going to avoid that. And so they're not going to allow that type of Ponzi scheme to happen in equilibrium, okay? And two, we also know that in equilibrium, because we only have one way of transferring assets intertemporally, the family's asset position has to be equal to the capital stock. So running up a huge negative asset position is going to violate the feasibility constraint on capital. Capital can't be negative. So what I'm trying to say here is that this problem with this sequential or period by period budget constraint is not there. It's not strong enough. It's not there are not enough constraints on this model to rule out the possibility of these Ponzi games. Okay, we actually, in order to make this a well-posed problem, we need to impose an additional constraint on this problem compared to what we saw in the optimal growth model. Okay, now let me also point out one thing here that I'm going to take a brief aside on. Okay, it is also extremely important in this class of models for this sequential trading formulation in a dynamic competitive model to correspond to something called the Aero Debrew equilibrium, after a couple of famous guys you may have heard of before. Okay. What does that mean in English? The problem I'm describing here is one of sequential trades, right? You wake up at the beginning of period T, you have some wealth, AT, you go and work, you earn your wage, you earn your returns on that wealth, and you go out and you trade your income for some consumption and you eat. And then you go to sleep and you wake up the next day and you do the exact same thing, where you make your decisions to satisfy this period by period budget constraint. That's what we mean by sequential trading. This is important that you guys understand this, okay? It's a part of the economic environment here. In this class of models, it's critical that the sequential budget constraint be consistent with what would constrain a consumer or a planner in what's called an Aero Debrew economy. Now, what the hell is that? An Aero Debrew economy is an economy where instead of trades taking place sequentially, they all take place in date T is equal to 0 in the initial period. In other words, Tavoy, you know what your lifetime labor earnings are going to be, right? You know what your lifetime utility function is going to be. What you actually go out and do is you make trades, contingent trades in period 0 to finance your consumption spending over your entire lifetime. So in other words, all of the consumption savings decisions, instead of being made one period at a time, are made in the initial period, and then after that are just implemented throughout time. You guys see what I'm talking about there? So in that environment, what would be the income constraint that faces a decision maker? Not this sequential period by period budget constraint, but rather a lifetime budget constraint, which says what? That the present value of your lifetime consumption cannot exceed the present value of your lifetime labor earnings plus whatever your initial wealth is. That is what we call the lifetime budget constraint. And what we want is for this sequential budget constraint to be consistent with the correct Aero Debrew lifetime budget constraint. Unless we impose an additional constraint on this model, you don't get consistency between those two concepts. Okay? Again, I'll come back to more of this later today and in the next class. Now, there are two ways to proceed here. We can either impose what's called a natural debt limit on this problem as our extra constraint, or maybe I should say instead of and, or we can impose something called the no Ponzi condition directly. Now, the natural debt limit is widely used and is intuitively appealing. But in fact, the no Ponzi game condition is the one that is more theoretically rigorous and provides a more direct connection between the sequential budget constraint and this Aero Debrew lifetime budget constraint, which we're going to talk about later. I'm going to go through both of them. In fact, I'm going to derive the natural debt limit and use it in order to motivate the no Ponzi game condition. Okay. All right. How are we doing so far? Good. Let's talk about the natural debt limit. Okay, the natural debt limit requires that a family's asset position per worker, that is little at, never become so large, large in terms of a negative value, that would make it impossible for the representative household to pay off that debt, even if it henceforth chooses zero consumption for the rest of its life. In other words, the natural debt limit we can derive directly from the period by period budget constraint. If we think about what would be the maximum debt that a household could take on and eventually repay as time approaches infinity, if it elects to choose zero consumption for the rest of time and simply pay back the debt every single period. That's what's called the natural debt limit. If, Tavoy, we were modeling a financial sector here that was actually making loans to the household, a lender would never make a loan to a household here that exceeds the natural debt limit. Because even if the household chooses to eat nothing for the rest of eternity, the lender would never get the full amount of the loan back. That's what we mean by the natural debt limit, and we can derive it directly from the household's asset accumulation equation. Now you'll recall in aggregate form, AT plus 1 is equal to 1 plus R times AT. So that's the gross return to the family's assets in period T, plus wage income minus consumption spending. Let me solve this asset accumulation equation for AT. And you'll notice that it's equal to 1 over 1 plus RT times AT plus 1 minus WTLT minus CTLT. Now, let's assume that CT is equal to 0 forever, okay? What I want to do is I want to solve this equation here for AT plus 1 by scrolling this thing forward one period. So AT plus 1 would be equal to what? 1 over 1 plus RT plus 1 times AT plus 2 minus WT plus 1 LT plus 1. And again, CT is 0, so that's gone. Now what is, so I've scrolled this equation forward one period to solve it for AT plus 1. But we also know from the first equation that AT plus 1 is equal to this, right? So I can set this whole thing equal to 1 plus RT times AT plus WT times LT. Again, assuming CT is equal to 0. All right. Now what I want to do is take this equation and basically solve it for, I'm going to divide both sides by 1 plus RT and have AT plus 2 on the left-hand side and everything else on the right-hand side. So this becomes 1 over 1 plus RT times a 1 plus RT plus 1 times AT plus 2 is equal to AT plus WT LT over 1 plus RT plus WT plus 1 LT plus 1 over 1 plus RT over 1 plus RT plus 1. See what we have here? This is basically the present value of the family's assets at date T plus 2. That is in terms of date T dollars. This can be thought of as a discount factor, is equal to assets at period T plus what? The present discounted value of wages over period T and T plus 1. So the family's present value of the assets that it has at the beginning of period T plus 2 is equal to the wealth it had at the beginning of period T plus the present value of its labor earnings over the next 2 periods. All right. What is AT plus 2 equal to? Well, again, why don't we just go back to this equation and scroll it forward 2 periods this time? What you're going to get then is a 1 over 1 plus RT times a 1 plus RT plus 1 times 1 over 1 plus RT plus 2 times an AT plus 3 minus WT plus 2 LT plus 2 is equal to the right-hand side. So I'm going to go back to my original equation, scroll it forward 2 periods, and plug it in there. Now what I'm going to do is go back and write this in terms of AT plus 3. So this just becomes 1 over 1 plus RT, 1 plus RT plus 1, 1 plus RT plus 2 times AT plus 3 is equal to what? Time T wealth plus the present discounted value of wage income in the subsequent 3 periods. We're doing basically iterative substitution on the household's asset accumulation equation. Now, if I were to do this an infinite number of periods, hopefully you guys see the pattern here. What we're going to find is that the product from, let's say, j is equal to 0 to some cap t, we'll go out to cap t periods, of 1 over 1 plus r t plus j times a t plus cap t plus 1 is simply going to be equal to a little t plus the sum from, let's say, s is equal to 0 to cap t of the product from j is equal to 0 to s of 1 over 1 plus r t plus j times wt plus s lt plus s. So the family's asset position at the beginning of date cap t plus 1 in terms of its present discounted value, that's essentially what this is. It's a product of a bunch of inverse interest rates, is equal to date little t wealth plus the present discounted value of labor earnings from period little t all the way out to period cap t. Now let me just simplify this a little bit. Let's assume that initial wealth, or that is AT, is equal to 0. So there's no debt or no wealth initially. And let's take the limit as cap t approaches infinity. Okay, then we have that the limit as cap t approaches infinity of the product from j is equal to 0 to cap t, 1 over 1 plus r t plus j, a t plus cap t plus 1 is equal to 0 plus the sum from s is equal to 0 to infinity this time of the present discounted value of lifetime labor earnings. You guys see that? What is this term? A t plus cap t plus 1, as cap t goes to infinity, is the family's asset holdings way out in time, but in terms of their present discounted value, right? It's not the current value of those assets, but it's the present discounted value, right? The net present discounted value. That is the value in terms of date little t dollars of the family's asset position way out into the future. In other words, how much assets will the family have accumulated by then in present value terms? Well, if it starts with 0 initial wealth, it's just going to accumulate assets worth the total present discounted value of its lifetime labor. That is assuming that consumption is equal to 0 forever, right? Obviously, if this household is consuming some every period, its wealth way out at cap t is going to be less than its lifetime labor earnings. Whatever this sum is, I'm going to call it W bar t because it's determined as of date little t, the present value of all of those lifetime labor earnings. This is the natural debt limit. A lender would never agree to make a loan to the family that exceeds W bar because the family would never be able to repay all of that, even if it chose 0 consumption forever. So the natural debt limit then can be written as AT has to be bigger than or equal to negative W bar for all t. If a lender provided this amount of credit to the family, then the family would have to consume 0 for the rest of its life, for the rest of eternity, in order to pay off that loan. If any more was loaned, the family would be unable to pay it all back. That's the natural debt limit. Now, what does the natural debt limit look like in terms of its per capita variables? We want to be careful about that. So in other words, if we divide both of these guys by LT, right? What do we get? Well, the right-hand side is little at, but what does and the left-hand side we'll call, little w bar t, but how does that relate to this term here? Okay, let's be clear about this. I don't want y'all to mess up the math. So this particular sum, this infinite sum, what is it equal to? Let's write out what that sum is. Well, for s is equal to 0, it is, let's see, WTLT over 1 plus RT, right? For s is equal to 1, it's WT plus 1 LT plus 1 over 1 plus RT times 1 plus RT plus 1. For s is equal to 2, it's WT plus 2 LT plus 2 over 1 plus RT, 1 plus RT plus 1 times 1 plus RT plus 2, et cetera, et cetera, et cetera. Okay? Now, if we were to divide this thing by 1 over LT, or multiply by 1 over LT, then what happens to the right-hand side? Well, it becomes, let's see, WT over 1 plus RT, right? What does the second term look like? Well, you're going to have an LT plus 1 over an LT, right? So that's going to be a WT plus 1 times a 1 plus N over 1 plus RT, 1 plus RT plus 1. The third term would be a WT plus 2. LT plus 2 over LT is a 1 plus N squared over this interest rate term. Yada, yada, yada. To borrow a Seinfeld term. Okay, well, can I simplify that? This to me looks like the sum from s is equal to 0 to infinity of the product from j is equal to 0 to s of a 1 plus n over a 1 plus rt plus j times wt plus s, right? Each of these terms is multiplied by a 1 plus n raised to the power at the time we're in, with the exception of the first one, right? So basically what you're doing here, you can multiply the whole thing by a 1 plus n, but then you divide the whole thing by 1 plus n. So it's this sum over a 1 over 1 plus n. Right? So the negative value of this thing is exactly equal to, or I should say the positive value of this thing is equal to the natural debt limit on a per capita form. Right? So assets per worker then have to exceed negative W bar T. This is the intensive form of the natural debt limit. It's the negative net present discounted value of lifetime labor income. So what I'm trying to say here is that if we go back to that original sequence problem, one way to make that a well-posed maximization problem is to impose the natural debt limit, right? That would avoid this situation of households drawing up a huge amount of debt to simply roll over every period to finance an infinite amount of consumption. There is an alternative strategy called imposing just the no Ponzi game condition directly. This one is preferred because it provides a more direct link between the sequential budget constraints that we've been working with and the corresponding lifetime budget constraint in this Aero Debrew type of world that I talked about, where all trades take place in the initial period. And afterwards, everything is just essentially implemented based on those date zero plans. Okay. Now, what I would like to do is try to derive the no Ponzi condition and use the natural debt limit as kind of a motivation for it. All right. So you'll recall that from the last, let me just rewrite this equation. So on the last page, that the present value of the family's asset position at date cap t plus 1 was equal to the family's initial wealth plus the present value of lifetime labor earnings. Now there's a couple of modifications I've made to this equation, okay? The first thing you'll notice compared to the one on the last page is that I've set little t equal to 0, okay? So initial wealth is A0, and I've changed my s's to little t's. So don't get confused by that. But more importantly, I've reinserted consumption back into the equation. So if we imagine that the family here does not have to consume 0 forever, then if we do that iterative process to the budget constraint over time, this is what it's going to look like. The present discounted value of assets at the beginning of date cap t plus 1 should be equal to the family's initial wealth plus the present value of their labor earnings minus the present value of whatever they spend on consumption. Now, if I were to write this in per capita terms, then what do I need to do? Okay. So I've got an AT plus 1, and I've got some WTLTs and CTLTs. What I need to do is rewrite this equation in terms of intensive form variables. So in other words, I need to essentially divide both sides of this equation by L0. All right. So what is AT plus 1 over L0 equal to? Well, that's just AT plus 1 over LT plus 1 times LT plus 1 over LT, LT over LT minus 1, all the way down to L1 over L0, right? All of these guys cancel. So that is just little a t plus 1 times, how many of those L's terms do we have? Cap t plus 1 of them. So 1 plus n to the cap t plus 1. What about WTLT over L0? What is that equal to? Looks to me like that should be equal to WT times LT over LT minus 1, LT minus 1 over LT minus 2, times blah, 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 L1 over L0.
Can you scroll up?
Oh, sorry. All those things cancel, and you would be left with a WT times, I believe that's a 1 plus n raised to the little t. And therefore, CT LT over L0 should also be CT times 1 plus n to the little t. So if we take these terms here and substitute them back into the equation that we started with, we get that the product from j is equal to 0 to cap t, 1 over 1 plus rj, times, let's see, at plus 1 over L0 is a cap t plus 1 times 1 plus n to the cap t plus 1. Well, let me stop there for just a second. You'll notice that there's from j is equal to 0 to cap t, that's cap t plus 1 terms, right? So we could take that 1 plus n and stick it into the product here. And this just becomes 1 plus n over 1 plus rj from j is equal to 0 to cap t. That would be equal to little a0 plus the sum from t is equal to 0 to cap t, product from j is equal to 0 to little t. Now, let's see, WTLT over L0 has this 1 plus n to the little t term. Again, there are little t plus 1 of them in this product. So to bring this 1 plus n into the discount factor, you would have to divide the whole thing by a 1 over 1 plus n, like we did in the last calculation. So this would be a 1 plus n over a 1 plus rj. Oops. Times little wt minus ct. Look, I know these manipulations are a little confusing. I strongly encourage you to go back and verify them on your own, okay? These kinds of things, tricks that I do here, and then, multiplying through by a 1 over 1 plus n, that allows me to pull the 1 plus n to the t inside of the product. All of that makes my life easier later on, but you may not see exactly how it's done right now, so go back and work through those on your own. Okay, so this is where we are. Let me now take the limit as cap t approaches infinity to either side of this equation. Let me do one more trick that will make my life easier here too. And that is, I'm going to scroll the left hand, because I'm taking cap t out to infinity in this limit, I can actually scroll the period, the time back one period, and it makes no difference because I'm evaluating it as t approaches infinity. So this is the same as the limit as t approaches infinity from j is equal to 0 to t minus 1 of a cap t. Okay, so this is where I'm at right now. Let's imagine for a second that the economy ends at date t. Trying to provide some motivation about where the no Ponzi condition comes from. So we're dealing with an economy that has a large number of periods, but a finite set of periods. Okay, and so at the beginning of date t, the world comes to an end. Okay, now a terminal condition we're going to have to impose on the equilibrium of this setup would be that the family cannot have debt at the beginning of date t. Right? The family has to have at least paid off all of its debts by the end of time. The sequential budget constraint that we've been talking about from the beginning of this class, however, does not guarantee that a cap t is going to be positive in equilibrium, right? And so what we have to do is we have to impose this as a constraint on the model. In a finite time model, that time ends at period t, we would have to impose on that model an additional constraint, which says that the family's asset position has to be non-negative at the end of time. The family can't go into the grave owing money to the financial intermediary, okay, or the bank, or whoever the lender is. So we need to impose this constraint on top of the model. All right, now notice that cap AT bigger than 0, of course, implies that little at has to be bigger than or equal to 0. Okay, now if little at is bigger than or equal to 0, then what does the right-hand side of this equation imply? Imagine instead of going to infinity, we just go to period cap t. If little at is bigger than or equal to 0, so if this left-hand side variable here is positive, or at least non-negative, 1 plus n over 1 plus rj, those are positive terms. That means the right-hand side has to be positive as well, right? So a cap t bigger than or equal to 0 implies that this term is bigger than or equal to 0. Now, what if I swing CT over to the right-hand side of this inequality? Then you're left with 1 over 1 plus n times the sum from 0 to cap t minus 1, product, j is equal to 0 to little t, 1 plus n over 1 plus rj, times CT would be less than or equal to initial wealth plus 1 over 1 plus n times the sum from t is equal to 0 to cap t minus 1, product, j is equal to 0 to little t, 1 plus n over 1 plus rj, times wt. What does this equation read to you? How do you interpret it? This is the present discounted value of lifetime consumption on a per worker basis cannot exceed initial wealth plus the present discounted value of lifetime wages. That is a lifetime budget constraint.
Can you restate what,
The left-hand side of this inequality is the present discounted value of lifetime consumption. It's the value of consumption from period 0 out to date cap t minus 1. Richard, you drop dead at the beginning of date cap t, so you don't get to consume in period cap t,
Okay.
right? This is the present value of your lifetime consumption, your stream of consumption over time. That has to be less than or equal to your initial asset holdings plus the present value of your lifetime wages. That is a lifetime budget constraint. If you guys go back to the 2-period OLG model and you plug the second period constraint into the first period constraint, right? Solve the second period constraint for S and shove that back into the first period constraint, what do you get? Consumption today plus the present value of your consumption tomorrow is going to be equal to your wage today plus the present value of your capital or interest earnings in the next period. In other words, the present value of your consumption has to be less than or equal to the present value of your lifetime earnings. It's the same concept here, right? But notice what we've imposed. In order to get the correct lifetime budget constraint, what do we have to impose? That cap T is bigger than or equal to 0. We had to impose that on the model. That constraint wasn't there initially. Now, my question to you is, what constraint do we need to impose on an infinite horizon model to generate the correct lifetime budget constraint? If we assume that the limit as cap t approaches infinity of the product from j is equal to 0 to cap t minus 1 of 1 plus n over 1 plus rj times a cap t, if we impose that this thing is bigger than or equal to 0, then what does that imply? That implies that the full right-hand side is bigger than or equal to 0, right? So a 0 plus 1 over 1 plus n times the sum from 0 to infinity this time, the product from j is equal to 0 to t, 1 plus n over 1 plus rj, times wt minus ct is bigger than or equal to 0. This equation can easily be rearranged to write 1 over 1 plus n times the sum from 0 to infinity of this discount factor term times ct is less than or equal to a 0 plus 1 over 1 plus n times the sum from t is equal to 0 to infinity of lifetime labor earnings in present value terms. That is the correct lifetime budget constraint for an infinite horizon problem. And what does it follow from? It follows from imposing what? From imposing this condition. If we assume that the left-hand side of this equation is strictly greater than or equal to 0, then we impose the correct lifetime budget constraint on this sequential trading problem. This is the no Ponzi condition. If I want to write this in terms of, instead of cap t, just in terms of little t, it can be written as the limit as little t goes to infinity of at times the product from j is equal to 0 to little t minus 1, 1 plus n over 1 plus rj. This is the no Ponzi game condition in its intensive form. So that sequential problem that faces the representative family in this model lacks the necessary constraints in order to rule out Ponzi games. If I impose this as an additional constraint on the model, then the sequential budget constraints in that environment will correspond exactly to the correct lifetime budget constraint in an Aero Debrew date zero trading environment. You get the same allocations, you get essentially the same constraints. The two are compatible with each other. Okay. So here's what we're going to do in the next class. We're going to characterize the full competitive equilibrium of this model. All right. It involves setting up and solving the representative household's maximization problem. What does that maximization problem look like? What I just showed you on the previous page, subject to one additional constraint, the no Ponzi game condition. Households take wages and rental rates as given. Another part of that equilibrium is firms choosing capital and labor optimally, taking wages and rental rates as given. Markets clear, just like in the OLG model. That's the full statement of the competitive equilibrium. So in order to characterize that equilibrium, what do we need to do? We need to write down and characterize the solution to the household's optimization problem here. That is, state the sequence problem, subject to these sequential budget constraints, but also subject to this no Ponzi condition, set up the value function, derive the optimality conditions that would then characterize the household's optimization problem, taking wages and interest rates as given. Combine that with the efficiency conditions for firms, that is the marginal product of capital is equal to the real rental rate, et cetera, and the relevant market clearing conditions in this economy, and then we can state the full competitive equilibrium. So that's what we're going to attempt to do in the next class. So we're going to want to apply our dynamic programming theorems to this particular model. Now, there will be a few differences that we have to adjust for, but it should be fairly straightforward. And then once we do that, we can characterize the steady state, do some comparative statics analysis. And then when we talk about the transitional dynamics in this economy, that's when we want to go and introduce a few new concepts like phase diagrams and the saddle path solution to the model. Okay, but that's not going to be until next week. All right, you guys have any questions about this? So spend some time really trying to understand the natural debt limit and this no Ponzi game condition. Try to understand kind of the economic environment and try to understand the similarities or the consistencies here between period by period trading versus date zero trading. All right, the allocations that come out of those two environments need to coincide with one another. And the only way to do that is to impose on the sequential problem the correct lifetime budget constraint, which is equivalent to imposing this no Ponzi game condition. So go through the steps of that and verify for yourself that you can arrive at this as an additional constraint. Are we good?